Hello everyone! I'm going to be doing a series of videos to hopefully provide some helpful tips for guys who'd like to learn more about electrical work. Man, the 2020 NEC book is a half-inch thicker than the 1999 book I had when I got licensed. And I changed careers in 2000 and didn't keep up with all the changes. So I've begun refreshing myself, and all my code references will be from the most current book. Right now, that's the 2020 NEC. It may seem like the last thing you might need to learn, but in this episode, I'm going to present a general overview of voltage drop and show you how to calculate the theoretical voltage drop for a circuit you're sizing, and discuss some relevant NEC articles and table references. I'm also going to show you an actual demonstration of voltage drop using a 4500 watt water heater as an example. I've watched a few other videos on this topic. For me, there's a better way to teach this subject than I've seen so far. You can decide which method you prefer, but my preferred method seems more intuitive. I think it's more relatable, so it's easier to understand and remember. Let's answer these three questions first. What is voltage drop? Why does voltage drop matter? What causes voltage drop? So, what is voltage drop? I think of voltage drop as wasted energy. But simply stated, it's the difference between the voltage present at the source and the voltage present at the point of use. So what causes voltage drop? There's no such thing as perfect conductors to wire our electrical power circuits with. Copper and aluminum are very good conductors, but they have some resistance. Okay, here's a sidebar. In alternating current systems, there's something called reactance. Resistance combines with reactance to create impedance. Impedance in AC circuits is much like resistance in DC circuits. Since reactance isn't generally a big factor in our power circuits, we'll keep it simple by mainly discussing resistance. So, although copper and aluminum are good conductors, because of their resistance, the longer the conductor, the more it acts like a resistor. And due to the resistance in circuit conductors, the voltage at electrical equipment will be less than the voltage of the power source. Why does voltage drop matter? Efficiency. If a circuit powers a large load, or a photovoltaic or other power generation system is deployed, minimizing voltage drop will recoup your investment many times over in unwasted energy. System performance. Lighting systems perform best when voltage drop is minimal. Voltage drop on long service conductors can cause lighting in the building to flicker when appliances or heating or cooling systems turn on. You'll also see this in outbuildings where a large motor starting can cause lights to flicker during the motor inrush period. Load protection. Under voltage on inductive loads can cause overheating of components and a shorter equipment life cycle. Under voltage on electronic equipment like computers and laser printers can cause them to lock up and suddenly power down, resulting in data loss and possible equipment failure. Voltage drop can cause inductive loads like motors and ballasts to operate below their voltage rating, which can cause them to overheat, which would result in shorter equipment life and increased cost. It could be a long-term troubleshooting aid. If a circuit's design voltage is up to par, that eliminates one questionable variable when troubleshooting an equipment problem. Any good explanation of voltage drop begins with Ohm's Law. And since almost every tradesman working with electricity needs to be familiar with Ohm's Law, this method is easier to understand and remember without having to memorize any new formulas or constant values. Because it's based on Ohm's Law and middle school level math fundamentals. E equals I times R. Okay, that's all there is to it. Thank you for watching. See you next time. Just kidding. If you aren't familiar with Ohm's Law, here's a short and sweet explanation. Ohm's Law states that the current flowing through any resistor is directly proportional to the voltage applied to its ends. Mathematically, Ohm's Law is expressed as E equals I times R, where E stands for the electromotive force, which is commonly expressed as volts. I stands for Intensität, which is German for intensity. It's electrical current, and it's commonly expressed in amps. R stands for resistance, which is commonly called resistance, and it's commonly expressed in ohms. So Ohm's Law can be translated into American as volts equals amps times ohms. The voltage drop calculation is derived from this simple relationship. After you've done all the calculations you normally need to do to size a circuit and select the conductors and overcurrent protection device, good system design should compel you to consider voltage drop, and the NEC promotes doing that. The first code references are Articles 210.19a and 215.2a1. 210.19 Conductors, Minimum Size and Ampacity. We're looking at A, branch circuits not more than 600 volts. So this applies to all our home branch circuits. The relative item here is Informational Note 3. Conductors for branch circuits, as defined in Article 100, sized to prevent a voltage drop exceeding 3% at the farthest outlet of power, heating, and lighting loads, or combinations of such loads, and where the maximum total voltage drop on both feeders and branch circuits to the farthest outlet does not exceed 5%, provide reasonable efficiency of operation. And then it actually refers us to 215.2a1, which I mentioned, and we'll go look at that. And so here it is, 215.2, minimum rating and size, A, feeders not more than 1,000 volts. So again, this applies to all the circuits we work on in our homes. And now I'm going to skip down past exceptions number 1, 2, and 3 and make my way, it's actually the next page, Informational Note number 2. And it says, conductors for feeders, as defined in Article 100, sized to prevent a voltage drop exceeding 3% at the farthest outlet of power. There's a typo there. Sized to prevent a voltage drop exceeding 3% at the farthest outlet of power, heating, and lighting loads, or combinations of such loads, and where the maximum total voltage drop on both feeders and branch circuits to the farthest outlet does not exceed 5%, will provide reasonable efficiency of operation. So there's a couple things we can gather from these informational notes. For one thing, they're not requiring us, in general, to size our conductors to minimize voltage drop. However, there are some specialized areas in the code, like for fire pump motors, where there are specific voltage drop requirements for those circuits. Those are in Article 695.7a and b. There are some other specialized voltage drop requirements as well. These are beyond the scope of this video. Basically, since their requirements are focused on safety, they're just recommending voltage drop minimization by promoting it in general terms. I'll say this for anyone involved in the alternative energy business or anyone who's thinking about installing, for example, solar energy, photovoltaic panels. Efficiency is incredibly important. You don't want to spend tens of thousands of dollars on your solar array and then lose more than 5% of your energy just because you installed conductors that are really too small because you have too much voltage drop. You're losing power when you lose voltage drop. So it doesn't make sense to spend thousands of dollars to generate power just to throw it away. So for photovoltaics, I would suggest you want to keep all your total voltage drop below 2%. It'll save you thousands of dollars in the long run. So another thing we can take from this is that they'd like us to limit our voltage drop on our feeders and or our branch circuit conductors to below 3%. And if you take the voltage drop on your feeders and you add it to the voltage drop on your branch conductors, you'll get better efficiency if the total length of your circuit combined is less than 5%, which makes good sense. And it's not just efficiency, it's also the way the system operates. Suppose you're out in an outbuilding that's far away from your main panel in your house, and you have a shop out there. You might fire up a big table saw and have your lights flickering because you didn't size your conductors properly. So minimizing voltage drop is efficient. It saves you money in the long run. And additionally, minimizing voltage drop can also protect your expensive appliances. If your voltage is too low, you're going to have components that start to heat up, and they just might not last as long. Okay, let's move on to my demonstration of voltage drop. In the following demonstration, I'll be using an old water heater as a test load. First, I'll connect it to my house's main service panel and take some voltage and current measurements on this 4,500 watt load. Then I'll take the water heater out to my pole barn and connect the water heater load to the barn sub panel. I'll take voltage and current measurements in both places for comparison. By the way, I'll have to put some water in the tank before powering it up. I happen to know that starting a water heater up dry will burn out the heater element within half a minute. Let's get started. Okay, I'm using a 40-gallon water heater to do this demonstration. It's rated at 4,500 watts at 240 volts. I'm filling the tank through the drain valve. I've connected temporary power with a 10-foot length of NM cable to a circuit breaker in my main panel. It's 10-3 with a ground, and only the black and red conductors are in use, with the white wire simply bent back out of the way. I'm using a 40 amp rated circuit breaker for this test. It's the lowest rated 2-pole breaker I have available right now. It'll be fine for this 5 minutes of testing. I would never do this on an actual installation. I added 2 short lengths of wire at the water heater terminations to use as test points. And that's basically 239 volts. Turn it back off. It's about 239 volts. It's roughly around 238.5 volts. Now let's see what we have on the main breaker. So it's at 243 volts unloaded. Switch the load on and we've got 239 volts, 239 and a half, something like that. And it goes back to 243. Try again. From 242 to 239. There's 3 volts of voltage drop just putting a load on that panel. That has to come from the service entrance conductors and the lateral leading up to them. Alright, we're hooked up to the water heater. Power's on. 239 volts. 238 plus. Okay, the amp clamp is hooked up. Okay, the circuit breaker is going on. You'll hear it click. The circuit breaker is turned on now, and there's current flowing through the water heating element. I've hung my amp clamp on a hot conductor. This amp clamp produces 1 millivolt per amp. We can see there's 18 millivolts on the meter, so that translates to 18 amps. At this point, let's do some math. The simple DC power formula is watts equals volts times amps. The water heater is rated at 4,500 watts at 240 volts. So 4,500 watts divided by 240 volts equals 18.75 amps. We saw that with our measured voltage at 238 volts, the water heater is drawing 18 amps. 238 volts times 18 amps equals 4,284 volt amps, or in air quotes, watts. So it can't be performing at its 4,500 watt rating. We lost over 200 watts of heating energy somewhere. This is our first indicator that voltage drop caused inefficiency and component misfunction. But here's a question for solar energy investors. Would you want to dissipate over 200 watts of power just in your wires? Think of it as losing all the power from one 200 watt PV module. And as we're about to see, it gets much worse as our conductors get longer. The barn is more than 100 feet from the front of the garage. The barn feeder starts at the southeast corner of the cellar. It exits the northwest corner of the cellar, right under where I'm standing on the deck, in this picture. So I'm guesstimating it's over 175 feet long, maybe close to 200 feet. The entire feeder was run with number 2 aluminum. For the next voltage drop test, I started by hooking my voltmeter to the barn feeder circuit breaker in the main panel. It starts out at 241 plus volts, but we'll see it drop when the water heater load is turned on, down at the barn sub panel. So here's the setup. I used that same 10-foot piece of, it's actually an NM cable. It's 10-3 with a ground, but I only used the red and the black. The neutral is just unused. The white wire is unused. And right now, with that breaker turned on, $237 volts. Okay, I'm going to go energize the circuit. $237 volts down here. You can see how I have it wired up here. Now let's measure current. Let me energize it first. Now I'll clamp it up. Got 17 amps of current down here. It must be all that extra resistance is reducing the current flow, because I had 18 amps up by the main panel. By the way, this is a Fluke I410 AC/DC current clamp. I don't know if you can see it clearly enough. Output 1 millivolt per amp. So we don't lose much voltage drop through this short 10-foot piece of cable, obviously. And here's the proof of that. Here's what we learned from this voltage drop demonstration. For one thing, I lost 6 volts from the unloaded main breaker to the barn sub panel, loaded at 17 amps. The amazing thing is, that's only 2.6% total voltage drop, so it's acceptable. With the heater hooked up in the cellar, we found out the conductors were dissipating over 200 watts. That's a significant waste of energy. But over by the barn, the water heater was operating at 4,032 watts. That's 467 watts below rating. That's more than 10% below the water heater's power rating. Why does that matter? Well, where's all that energy going? That's 467 watts of heat energy being dissipated by your circuit conductors. Imagine what that costs over time. Imagine how much money you'd be losing over 20 years if that was your solar energy system. I mean, think about it. Thank you for joining me for part 1 of, what, the voltage drop? Please go over to part 2, where I'll get right into doing voltage drop calculations. Thank you for watching. Hey, before we go, I'd like to invite my subscribers to receive my free Excel spreadsheet-based voltage drop calculator. Just send me an email at the address in my channel contact information. If I can see you in my subscribers list, I'll send it right out to you. This is a limited time offer, but the time limit is informal, so there's a lot of flexibility there. And you might like to have it to follow along in part 2 of, what, the voltage drop? I'll be showing you how it works and how helpful it can be when you're designing a new power circuit. It's also filled with additional user aids as well. Okay, catch you later.